InterFET, the low noise JFET specialist. In this video, we will see how a JFET can be used as a voltage controlled resistor. Let's form a circuit with a JFET, shown here, and a variable power supply. By connecting the positive connection of the power supply to the drain of the JFET and the negative of the power supply to the source, we can create a current in the direction shown by the arrow. Notice that we have connected the gate of the JFET to the source of the JFET. This will cause it to have the least amount of resistance between the drain and source. We will measure the drain current with a meter and call it ID. It will vary depending on the voltage provided by the variable supply. When current flows through the JFET from drain to source, there will be a measurable voltage across the JFET channel that exists between the drain and the source. We will call this voltage VDS. In the simple case, VDS will be equal to the supply voltage since there is no other circuit element in the loop to drop any voltage. Let's chart the change in the current as we vary the voltage. Since we are controlling the voltage, it will be on the X, or horizontal axis, and the current that results will be on the Y, or vertical axis. Notice how the current starts up at a steep angle and then turns and runs at a shallow angle. This is the characteristic curve for JFET. The area where the curve is steep is called the ohmic region because it is like a resistor, and the area where it is shallow is called the saturation region because increases in voltage do not cause much of a change in current. This curve results when the voltage between the gate and source is zero. Let's see what happens when we remove the short between the gate and source and replace it with another variable supply. Notice that the gate is connected to the negative rail of the supply. Let's set the gate supply to minus 0.3 volts and again vary the drain voltage between 0 and 10 volts. This time the current has a similar shape but is lower, and the ohmic region is not as steep as it was when the gate to source voltage was at 0 volts. If we run the test again with the gate to source voltage at negative 0.2 and negative 0.1, we will find intermediate curves. To use the JFET as a voltage control resistor, we will be operating in the ohmic region where the curve is steep. Let's expand that region and concentrate on two of the curves. We can calculate the effective resistance between the drain and source by using the formula for resistance. Twinkle, twinkle, little star, V is equal to IR. Since the lines are now very close to straight, and they are a plot of current versus voltage, we can estimate the resistance by looking at the change in voltage and divide by the change in current. The resistance for the curve generated when the gate to source voltage was 0 has a resistance of about 10.5 ohms. If we repeat this process for the curve that was generated when the gate to source voltage was negative 0.3 volts, we get a resistance of about 16 ohms. We can readily see that increasing the magnitude of the negative gate to source voltage increases the resistance of the drain to source channel. This is how a JFET does all that it does. Let us now turn to a practical circuit. We'll start by evaluating a simple resistor divider with an applied sine wave. We can see that the bottom resistor, R1, is set to a value of Vc. This allows us to change it dynamically. The applied sine wave is 100 millivolts and 1000 Hz. If we measure the output voltage VO, we can see that it will be some fraction of the input sine wave. The fraction depends on the values of R1 and R2. When we run a transient analysis on this circuit and plot the output voltage VO while varying the value of R1 from 200 ohms to 1600 ohms, we can see that the output is a sine wave that is a fraction of the 100 millivolt input. As the resistance of the bottom resistor, R1, increases, the output sine wave amplitude increases. We can replace the bottom resistor with a JFET, the 2N4341 for example. We will apply a control voltage Vc to the gate from the source and vary this voltage from 0 volts to minus 4 volts. This will achieve the same effect as changing the resistance without having to manually change a resistor or adjust a potentiometer. As the control voltage is varied, the resistance between the drain and source changes and controls the fraction of the input voltage that makes it to the output. The minimum output occurs when the control voltage is 0 because that is when the drain to source resistance is minimum. Note that the waveforms are symmetrical and appear to be sine wave shapes. There are a few things to consider when designing a voltage-controlled resistor circuit. The first is that the input voltage must not exceed the forward bias limits for the JFET. To see why, look at this basic drawing of an N-channel JFET structure. A substrate of P-type semiconductor material has a layer of N-type epitaxy grown on top. Connections for the source and drain are attached at different places on the surface to form a channel in the N-type epilayer. Then the gate structure is embedded into the N-type epilayer, but it is made of P-type semiconductor and is connected to the substrate. There are only two types of semiconductor material here, P-type and N-type. This forms a diode. The anode is the gate and substrate, and the cathode is the channel between the source and drain. If this diode is forward biased without some form of current limit, the JFET can be destroyed. Another thing to consider is distortion. Remember that the lines in the ohmic region change from mostly vertical to mostly horizontal. If the input signal peak excursions are too much, they raise the drain voltage too high, where the resistance is not a straight line and the result is distortion. This is possible on both the positive signal highs and on the negative signal lows. Back in QSpice, we had an input sine wave that was 100 millivolt peak. What happens if the input signal is larger? Let's simulate the same circuit with a 2 volt input signal. Here we can see that the sine wave is distorted. It is quite noticeable here on the negative part of the cycle, where it looks flat. The peak signal is reaching almost 2 volts. Distortion on the positive half cycle is harder to tell. Luckily, there is something we can do about this distortion. We will add 2 resistors to the circuit. These will create a resistor divider that will couple part of the drain signal back to the gate. The resistors are equal in value, so both positive and negative signals are connected equally. Looking at the simulation results, the distortion is gone, but the amplitude is now about half. This is the price to be paid, but it is usually worth it since many designs have larger signals to begin with. I hope you found this video to be informative and perhaps a little entertaining. There is, of course, more to learn about voltage control resistors. And for more details on using a JFET as a VCR, please see the InterFET website and use the support pull-down to find app notes. Then scroll down to FETs as voltage control resistors. Thanks for listening. Hope you enjoyed it. If you enjoyed this video, give it a thumbs up and subscribe for more expert insights into JFETs, analog design, and low-power electronics. Hit the bell icon so you never miss an update from InterFET. Got questions or ideas for future videos? Drop them in the comments. We'd love to hear from you. Interested in using JFETs in your next project? Reach out to us directly through our website or the link in the description to speak with our team of experts. Stay connected, stay curious, and keep innovating with InterFET.